Hey everyone, Carl here. Today, I want to tell you about a liquid that terrifies even the world's most advanced scientists. A substance so reactive, so uncontrollable, that moving it from one place to another can trigger catastrophic explosions. This isn't science fiction. It's real, it exists, and it's inside our planet, and sometimes inside our laboratories. This is the story of the world's most dangerous liquid. When we think of dangerous liquids, our minds often conjure images straight from fiction. We imagine bubbling, neon green acids capable of melting through solid steel in seconds, or perhaps barrels of eerie, glowing nuclear waste pulsing with unseen radiation. These are the classic symbols of chemical peril, ingrained in our collective consciousness by decades of cinema and storytelling. They represent a straightforward, almost cartoonish form of danger, a simple cause and effect. Touch the acid, you get burned. Stand near the waste, you get irradiated. But the reality of chemical danger is far more complex and infinitely more fascinating. The true measure of a liquid's hazardous nature isn't always its inherent toxicity or corrosivity. While those properties are certainly perilous, the most catastrophic chemical incidents are often born from a different, more volatile characteristic. The true danger lies in instability. It's a concept that governs how a substance behaves when it's disturbed, when it's touched, moved, heated, or even just looked at the wrong way. Think of it like this. A stable liquid is like a heavy book lying flat on a table. You can nudge it, shake the table, and it remains largely unchanged. It is in its lowest energy state, content and predictable. An unstable liquid, however, is like a book balanced precariously on its edge. It is in a high energy state, brimming with potential. The slightest disturbance, a gentle breeze, a minor vibration, a subtle shift in temperature, can be enough to send it toppling over. But when an unstable chemical topples over, it doesn't just fall. It releases all that stored potential energy in an instant, often with explosive and devastating consequences. Some liquids are so profoundly unstable that they exist on a knife's edge between their liquid state and violent decomposition. For these substances, the normal, everyday fluctuations of our world are a constant threat. A 1-degree change in ambient temperature can initiate a runaway reaction. The subtle vibration from a nearby piece of machinery can be the catalyst for detonation. Even exposure to sunlight can provide the activation energy needed to unleash chaos. These are not just liquids, they are caged beasts, and their containers are the only thing keeping their fury in check. Among this class of hyperreactive compounds, one substance stands out for its legendary and terrifying properties. It is a chemical so volatile, so aggressive, that even seasoned chemists speak of it with a unique mixture of awe and dread. During the Second World War, German scientists tasked with weaponizing it nicknamed it Substanz N, or Substance N. Its true name is chlorine trifluoride, or ClF3. To say that chlorine trifluoride is flammable is a profound understatement. Flammability implies that a substance needs oxygen to burn. ClF3 does not. In fact, it is such a powerful oxidizing agent that it can make materials we consider completely non-combustible burst into flame. It can set fire to asbestos, a material used for fireproofing. It can ignite glass, sand, and concrete. It is so reactive that it will burn through materials that have already been burned. It can set fire to ash. The infamous chemist John D. Clarke, in his book Ignition, described it perfectly. It is, of course, extremely toxic, but that's the least of the problem. It is hypergolic with every known fuel, and so rapidly hypergolic that no ignition delay has ever been measured. It is also hypergolic with such things as cloth, wood, and test engineers, not to mention asbestos, sand, and water, with which it reacts explosively. Yes, sand. A substance made of silicon dioxide, one of the most stable compounds on Earth, becomes fuel for the fury of chlorine trifluoride. But even this doesn't capture the full horror of its chemistry. It doesn't just burn things in the conventional sense. It attacks them on a fundamental atomic level. ClF3 is one of the most powerful fluorinating agents known to science. This means it has an insatiable hunger for electrons, and it will rip them away from nearly any other molecule it encounters in a process called oxidation. This is not a gentle transfer, it is a violent theft. When chlorine trifluoride touches a substance, it doesn't just heat it up, it chemically dismantles it, tearing atoms apart to get at their electrons, releasing enormous amounts of energy in the process. This is why it can make the unburnable burn. It forces other materials to oxidize, whether they want to or not. That means water, skin, metal, everything becomes fuel. A reaction with water is particularly violent as the ClF3 boils the water instantly while simultaneously ripping it apart into a toxic cocktail of hydrofluoric acid, hydrochloric acid, and free oxygen, which then acts as an accelerant for the fire. It is a substance that defies our most basic assumptions about the world. It is a liquid that wages war on matter itself, and understanding it is the first step in understanding the true hidden dangers that lurk within the world of chemistry. In World War II, German scientists stumbled upon a substance of almost supernatural destructive power, chlorine trifluoride, or ClF3. They sought a weapon, but found a curse. One of the most powerful oxidizing agents known, it sets fire to sand, glass, and even concrete. During one infamous incident, a 1-ton spill burned through a foot of concrete and 3 feet of gravel beneath. The Germans abandoned the project, deeming it too treacherous to handle. It creates what chemists grimly call an everything fire. So why do we keep such a volatile demon in our toolkit? Because in the semiconductor industry, it performs a task almost nothing else can. The microscopic circuits inside our phones and computers are made in chambers that must be perfectly clean. Chlorine trifluoride is used as a gas phase cleaning agent, reacting with unwanted residue and leaving the chambers atomically clean. Its efficiency is indispensable, a necessary evil that helps build the very foundations of our digital world. And ClF3 isn't alone. There are other liquids that could turn your stomach inside out. For instance, hydrazine, used as rocket fuel, is so toxic that NASA engineers wear full-body suits to handle it. Just a few drops on skin can cause seizures or death. Then there's fluoroantimonic acid, the strongest acid known to science. It's so powerful, it can melt glass, plastic, even dissolve your bones before you feel pain. And yet, these liquids help us explore the stars, build technology, and understand chemistry itself. Transporting these liquids is like moving a sleeping dragon. You can't wake it, bump it, or let it sense warmth. Trucks carrying such materials are often escorted by safety teams. Every bump in the road, every temperature shift is monitored, because one mistake, one micro crack in a pipeline, could unleash invisible death clouds for kilometers. That's why many of these liquids are never transported at all. They're made and used in the same place, under total control. Here's the paradox. Humanity keeps inventing things too powerful for itself. We create energy, chemicals, and technologies that defy safety, all in the name of progress. We've learned to control some of them. Others control us. And every breakthrough comes with a warning. Just because we can create something doesn't mean we should. Dramatic pause. Soft echo of should. So next time you see a tiny computer chip or watch a rocket launch, remember, somewhere deep inside those achievements lies a liquid too dangerous to move, yet powerful enough to change the world. I'm Carl. And if you want to keep exploring the strange side of science, hit that subscribe button. Because here, curiosity is always dangerous.